Hi, today I'm going to talk about the physics underlying the interesting theme of the Faraday cage. This is the cage that was apparently first built by Michael Faraday using a crisscross of metallic wires, and as he was put himself inside that wire cage, he found that the strong electric field from outside the cage was not able to penetrate to his body that was inside the cage, and that was quite a fantastic phenomenon that he observed. Actually, this also became one of the great applications of the physics of electromagnetism. Whenever some secret agency wants to put you in a room without any wireless connection, the room is surrounded by some metallic wire network so that the wireless signals from the antennas cannot possibly penetrate to the inside and reach the cell phone that you have. Okay, so that's the Faraday cage, and we're gonna look into the physics and mathematics of that device by solving a model problem, which is a bit simplified version of what the real Faraday cage will look like. So we have a array of wires. It looks like a dot, but each dot is really a wire that's extending in to infinite extent in the third direction. So one should really think of this dot as a cross section of an infinitely long wire that has uniform charge density lambda on it. And these wires are placed at regular intervals of separation A. And we have two such layers, one layer at the bottom like this, another layer at the top, and they're separated by the distance of d. So presumably a person living inside in between the two layers, for example, in this region, will have little experience of the electric field because of the shielding coming from these wires. Okay, so how do we solve this problem? Well, we'll try to solve the problem of the potential produced by these array of wires. And in order to do that, let us first recall the solution of a single wire like this. If there's a uniform charge sitting on top of this wire of lambda, then the potential produced by such a wire is this function log of r. I think we solved this problem back when we were talking about Gauss law, and I hope this is a good chance to remind yourself of that solution. It's also useful to remind yourself that this solution indeed satisfies the Laplace equation as it should, because away from the wire there's no charge, and therefore the Laplace equation must hold. So this particular solution must also be consistent with the Laplace equation. And verifying this would be one of the homework exercises that accompany your summary of this lecture. Okay, so I'll be keeping an eye on that. If you don't produce a solution, then you might get a deduction. Actually, you will get a deduction. So let's keep that in mind. Okay, so now we move away from that simple solution and ask, what is the potential produced by an infinite array of wires with a separation A between the adjacent wires? Okay. Well, well, the answer must be still in this Laplace equation. Uh, and in addition, we already know, without even having to solve this problem, that this solution, whatever the form may be, must obey this periodic periodic condition, because these potential sources are placed at periodic intervals. Okay, so the potential produced by such a periodic array will also be periodic. There's no escaping that conclusion. And secondly, if you move far away from this array, either in the plus y or minus y direction, then then the potential should presumably decay. Okay. Actually, this statement is not completely true, but I'll put that out here anyway, and then later argue that there's a small loophole in this argument. And I will also show you how to fix that loophole. Okay, so the general expectation is that we want a solution that is oscillatory in the x direction, but exponential in the y direction. And from our previous experience of solving the Laplace equation in the rectangular coordinate system, by the separation of variables technique, we know that these choice of the x function part and this choice of the y function part should yield a oscillatory solution, sines and cosines for the x function, but exponential function for the y function. Okay, so that's the physically motivated and physically reasonable choice of the sign of this constant. So first of all, when k is 0, then this solution, which is a product of the x function and the y function, would be of this form, some constant plus b, another constant times y. And I put a magnitude absolute value sign here because, again, on physical grounds, it should be obvious that um, the potential should really only depend on the distance from where the array is located. And so it's only appropriate that we put this magnitude sign around the y coordinate. And for k not equal to 0, as promised, we have some cosine function multiplied by an exponential function. Well, more generally, you should choose the linear combination of the cosine and sine, but through using the addition rule of cosine functions, we know that this general combination basically just reduces the cosine of kx after some suitable redefinition of the coordinates. So let's not bother to go through too much generality because we know that the answer will eventually come down to this one. Okay. 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 Again, I put an absolute sign here because, as I said, this function better fall off exponentially as you move away from the array, and this absolute sign here guarantees that exponential fall off. Okay, so putting all those elements together, we know that the general form of the potential must be like this, where it's a summation over over the k's. There's no restriction on the k values yet. So what we are going to do is to start uh, making more and more restrictions uh, that are physically motivated, and using those restrictions to constrain the values of these coefficients a, b, and ck. Well, first of all, uh, let me solve this problem first. There's a periodicity of the potential along the x direction, which is only guaranteed if this condition is satisfied. That is, every time you move x by an amount of a, then the function becomes equal to itself. That will only be guaranteed if this was equal to 1, which will only be guaranteed if k was quantized, like this. Okay, so this function now takes on a slightly more concrete form, where k is no longer an arbitrary value, but it's something that is quantized in integer multiples of 2 pi over the separation between the adjacent wires. Okay, and we can choose m to be positive, because negative m does not, well, actually, first of all, negative m means this will be an exponentially growing function, which does not make sense physically, so that is automatically ruled out. And now, secondly, there's this thing here. I said that the potential should fall off exponentially as you move away from the layers, from the array of wires. But this one is not really exponentially falling. It's actually linearly growing potential. So why do we have to keep this thing? Well, there's a reason. Well, if you look at this array, then actually, when you look at this system from a distance far, far away, it should more or less look like a plate. So imagine you spread this charge around, and also spread this charge around until they touch each other and form a continuum. Then this discreteness of the charge will be gone, and instead give way to something that looks more like a continuous charge distribution. And this is exactly the situation of an infinite charged plate. And we know exactly what kind of potential is produced by an infinite charged plate. That's this guy over here, where this sigma, which now stands for the areal charge density, is related to the line charge density lambda divided by the separation. Okay, so based on this physical reasoning, we can only fix b to be this number and a to be 0. Okay, so now we are able to nail down the exact form of the potential slightly better, like this. And then you see that the only remaining job is to fix these coefficients Cm. So how do we do that? Well, there's something called a boundary condition matching in the electrostatics. And the condition says the potential across the boundary must be continuous. So first of all, let me clarify what I mean by a boundary in this problem. So you see already that these potentials are discontinuous. well, the functions are continuous, but obviously the derivatives are discontinuous across the y equal to 0 line. Okay, you can see that from all these absolute value signs over here. Okay, so I can think of this y equal to 0 line as the boundary. And I have some electric field that live on the y equal to plus side, uh, and I have some electric field that live on the y less than 0 side. And these two electric fields, or rather the potentials on each side, must somehow match across this boundary, which is at y equal to 0. And the potential itself cannot have a discontinuous jump across the boundary. That's against the laws of electrostatics. So therefore, the field, where is it? So the potential itself has to change continuously. But since the derivative of the potential is electric field, then electric field does not have to be continuous. Okay, rather the difference of the electric field exactly equals the charge density that lives on the boundary surface. So you can understand this condition by thinking back to the case of a uniformly charged plate with electric field that are coming out on either side. So electric fields suddenly switch directions as it goes from one side of the plate to the other side. And so electric field is discontinuously changing across the plate. But that's okay because that solution is still consistent with this boundary condition. Okay, so this statement here is just a generalization of this observation that we are already very well aware of in the case of a uniformly charged plate. Only the difference now is that this charge density is not some constant thing, but it's a series of delta functions. Because remember, this is still not a smooth charge distribution. The charges are localized strictly inside this dot. So the best way to represent such a charge distribution is through the use of the delta function. So this is the appropriate way to represent the charge distribution for that array of wires. And P is an integer that runs from minus infinity to plus infinity. Okay, so now we're finally ready to take some derivative and evaluate the derivative when y equals positive 0 from the positive side, and also when y equals 0 from the negative side. But it's not really necessary to separate these, to compute these derivatives separately at y equal to 0 plus and y equal to 0 minus, because they are, after all, the same value except for the change in the sign. So this difference comes out to be exactly this value. And I claim that the difference should match the potential, should match the surface charge density given by a series of delta functions. And so the point is that this coefficient m, Cm, must be chosen in such a way that this Fourier series must be able to reproduce the series of delta functions. Now, because this is a series of delta functions, this is still a periodic function. And according to the theory of Fourier analysis, any periodic function can be reproduced as a Fourier series, even the periodic function consisting of delta functions. So I leave it to you as a homework exercise to figure out what these coefficients are, Cm, and thereby complete the derivation of the potential form, which I have left here slightly unfinished. So that's the other piece of homework exercise problem that accompanies this lecture. So be sure to turn that in alongside with your report of the summary.